This is Dr. D. Govardhan, Professor and Head, Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today's topic is moment of inertia from the first principles. Now consider a rectangle having breadth is equal to B and depth is D as shown in figure. Okay, let us determine the moment of inertia of this rectangle about its base AB as well as its centroidal axis. That means the axis which is passing through the centroid. First consider a small strip having thickness dy at a distance of y from the central axis as shown in figure. Here central axis is represented as now the symmetrical reference lines, x-axis and the y-axis as shown in figure now. Consider segment now, dy, small area, infinite is small thickness now, dy at a distance of y from the central axis xx as shown in figure. The area of the strip is equal to, since the having thickness is equal to dy, assume it is equal to dA. dA is equal to y into dy now. Sorry, dA is equal to breadth into dy now. That is here B is representing the breadth or the width of the strip and dy is representing its thickness. That is the product of length and thickness, that is B into dy. It is represented. We know that the moment of inertia of this strip about the x-axis is given by the product of area multiplied by the square of the distance between them. That is area is equal to, already we have taken dA is equal to B into dy now. The distance between the strip as well as the x-axis, it is a y is given now. That is, it is equal to area multiplied by the square of the distance. Area is equal to B into dy and y is the distance between the two parallel lines, that is y square now. Or it is equal to B constant y square dy now. Then the moment of inertia of that entire section about a line xx, that is central axis, is obtained by doing the integration of b y square dy from the limits minus d by 2 to plus d by 2. Because we have taken here now, this is known as the axis now. Above the length is given by d by 2. Here below also it is there now d by 2. Hence we are doing the integration from axis to top as well as from the axis to from the bottom now. That is the total area now. That is limits now becomes minus d by 2 to plus d by 2 now. That is I-axis is equal to that integration of minus d by 2 to plus d by 2 b into y square dy now. Where b is representing the breadth of the rectangle, it is always constant now. The remaining is b into integration of minus d by 2 to plus d by 2 y square dy now. Or which is equal to b into y square integration is, that is b is the constant now. Integration of y square dy is equal to b into y cube divided by 3. The limits are given minus d by 2 to plus d by 2. And substituting these values of limits in the above equation, we got it now. B into d by 2 cube whole cube by 3 minus of minus d by 2 whole cube divided by 3 now. So from this equations we got it is equal to b d cube by 12 now. That is the moment of inertia of a rectangular plate or rectangular section. It is equal to the, that is about its central axis, IgG is equal to, we got B dq by 12 now. That is here it is given like this. That is B, D since it is dividing, it is equal to D by cube divided by 12 we have to take. Similarly, in order to determine the moment of inertia about the rectangular plate about y-axis, it is equal to Iyy is equal to, it is given by, here while just taking y-axis, it is now dividing the breadth into parts now, and so we can take D into BQ by and 12 now. Now according to the parallax theorem, the moment of inertia of this entire area about an z-axis, which is passing through the intersection of x-axis and y-axis and passing through central axis. Here now, according to this figure, Izz is equal to, we can take it as Ixx plus Iyy. This is our required answer now. Now sometimes it is also required to determine the moment of inertia of that entire section about the line AB or about its base AB now. So in order to determine, we have to use Parallax theorem. According to the Parallax theorem, let the moment of inertia of that entire area about its central axis Ix, if it is represented as Igg, the moment of inertia about base AB is represented as IAB. The distance between these two parallel lines is represented now equal to D by 2 now. According to the parallax theorem, the moment of inertia of about any line AB is equal to the sum of the moment of inertia of that entire area about the central axis which is parallel to AB and area multiplied by the square of the distance between these two lines. That is IAB is equal to Ixx plus area multiplied by the square of the distance AH square now. Where Ix is equal to representing the Ig, that is the moment of inertia of that plane area about its central axis which is parallel to AB now. A representing the area of the rectangle now, which is equal to the product of breadth and depth B into D now. H is representing the distance between the line AB and central axis, which is equal to half of the depth, that is D by 2 now. Now substituting all the values in the equation number 1 here, which is represented now, that is IAB is equal to BDQ by 12 plus BD into D by 2 whole square now, which is equal to BDQ by 12 plus BD by 4 now, BDQ by 4. This in these equations, the 12 is the LCM now. Here BDQ by plus here now 3BD divided by 12 now, which is equal to 4BDQ by 12, which is equal to BDQ by 3 now. That is the moment of inertia of that entire rectangle about its base AB is given by BDQ by 3 now. Similarly, the moment of inertia of that entire area about a line AC, the vertical line, is given by D B cube divided by 3 now. So these are the equations generally used to determine the moment of inertia of the plane area about its basis or centroidal axis. The second method, directly we can determine the moment of inertia of the entire area about its base AB. Now consider the sections ABCD having B is equal to breadth and D is equal to depth. Let OX and OY is representing the reference lines as shown in figure. Now consider a steep. First let us find the moment of inertia of that entire area about a line AB, which is here represented as a x-axis now. Let us consider a strip which is having thickness is equal to dy at a distance of dy. Let us consider a small strip PQ having thickness is equal to dy at a distance of y from the line AB as shown in figure. The area of the strip is equal to product of breadth multiplied by its thickness, that is dA is equal to, we can take it as BDY now. The moment of inertia possessed by this element about a line AB, which is at a distance of y as shown in figure, is given by the product of area and the square of the distance between the lines now. That is the area multiplied by the square of the distance. Area is given by B dy y square, B dy, and area square of the distance is equal to y square. From this relation we got to B y square dy now. The moment of inertia possessed by that entire area about a line AB is obtained by doing the integration from AB to DC, that is from the limits 0 to D. The equation is B y square dy now. Where B is representing the breadth now, it is a constant now. The modified equation is, we can take it as 0 to D, B is a constant, is equal to, that is y square into y into dy now, which is equal to B constant 0 to D, y square dy as shown in figure. So total inertia is obtained by doing the integration from 0 to D. Since B is a constant, y square dy, the integration is y cube by 3. So it now becomes, after applying limits B into y cube by 3, 0 to D now, on substituting we got to B d cube by 3. It is nothing but similar to the values which is obtained after applying Parallax theorem for the previous problem now. Similarly, Iyy is equal to dB cube by 3 now. Now, the moment of inertia possessed by the element about its central axis is obtained. That is, if it is a GG there, by using the equations, IAB is equal to, we got it to IGG plus A into H square, that is nothing but distance between the two lines H1 square now. So IGG is equal to, we can take it as IAB minus half AH1 square, where H1 is stand for the distance between the central axis and AB, which is equal to half of the depth now. So substituting these values, the equation now, Ig is equal to Ix minus H square now, we got Ig is equal to BD cube by 12, which is nothing but similar to the previous problem. So you can use any one method to determine the position of, to determine the values of moment of inertia possessed by the area about its base as well as the centroidal axis now. Similarly, the moment of inertia of a hollow rectangular section, let capital B is representing the breadth of outer rectangle, capital D is representing depth of the outer rectangle as shown in figure. Here capital B and capital D now. Or here we are representing capital B and capital D now. And lowercase letters B and D is representing the breadth as well as the depth of inner rectangle or cutout rectangle as shown in figure now. Now, according to the previous derivations, the moment of inertia possessed by the outer rectangle about the central axis, that is the x-axis, is given by BdQ by 12 now. BdQ by 12. Similarly, the moment of inertia possessed by the cutout rectangle, that is inner rectangle, HGEF, that is this rectangle EF, GH, it is given by BdQ by 12 now. So, the moment of inertia of hollow rectangular section about x-axis is given by BdQ by 12, that is the difference of moment of inertia possessed by outer rectangle and inner rectangle, that is difference values, it is equal to BdQ by 12 minus BdQ by 12, it is shown in figure. Similarly, the about the y-axis is given by dBQ by 12 minus of lowercase letters dBQ by 12. These equations are old school for a rectangle to determine the moment of inertia at its base also now. And these two equations, these are old good for a rectangle, particularly whose central gravity is constant with each other. Now consider circle, the moment of inertia of a circular section. Consider circle ABCD, A, B, C, D with the center O, and X and YY is representing the central axis passing through the central gravity of the given object, which are again perpendicular to each other now. Now we have to represent the central gravity of moment of inertia of that entire circle about an horizontal axis, that is x dash x as well as the y dash y as shown in figure now. In order to determine the moment of inertia of the circle, first we are considering about z axis. The z axis means here now the axis which is the perpendicular to the x and y axis. Here z axis. Let us consider a ring of thickness is equal to dr at a distance r from the center of the circle as shown in figure now. The area possessed by this circle at z axis is given by the area multiplied by the square of the distance. Here area is equal to circumference of the circle we have to consider, which is equal to 2 pi r multiplied by the thickness, which is equal to 2 pi r into dr. This is nothing but area multiplied by the square of the distance r square, that is 2 pi r cube dr. The moment of inertia of that entire circle about the z axis is obtained by doing the above integration above equation from the limits 0 to capital R, where capital R is representing the radius of the given circle So Iz is equal to integration from 0 to r now 2 pi r cube into dr, which is equal to 2 pi is the constant now. We can written as the remaining equations 0 to r cube into dr. Again, after integrations 2 pi r cube dr integration is r by 4 r to the power of 4 divided by 4, having the limits 0 to r now. So now applying, we got this equation is equal to 2 pi r to the power of 4, capital R to the power of 4 divided by 4. It is equal to pi r to the power of 4 divided by 2 now. That is the Iz. But if d the diameter now, which is equal to twice of its radius 2r, and substitute these values are in this equation now, we got it is equal to pi d to the power of 4 by 32 now. This pi d to the power of 4 by 32 is representing the moment of inertia of that entire circular plate about the z-axis. That means I, Z, Z, we got it now. But according to the parallax theorem, Iz is equal to Ixx plus Iyy. That means the moment of inertia possessed by that circular plate about the z-axis, it is equal to the sum of the moment of inertia possessed by the same element about the x-axis and the y-axis, which are passing through that z-axis now. That is intersection of the z-axis now. So Iz is equal to Ixx plus Iyy. Since the object is symmetrical about the x-axis as well as the y-axis, hence it can be written as now 2Ixx r is also equal to 2Iyy now. Hence Ixx is equal to Iyy, which is also equal to Izz divided by 2 now. That means according to this figure now, Ix is equal to Iyy, which is equal to Izz by 2 now. Izz is equal to pi d to the power of 4 divided by 32 by 2 is equal to pi d to the power of 4 by 64. This is our required answer now. The moment of inertia of a hollow circular section now. Now let us consider a circular section which is having center as O represented now, and with d the diameter of outer circle, that is the main circle, and the small d is representing the diameter of the cutout circle now. According to the previous equations, the moment of inertia possessed by the main circle, which is having capital D as the diameter, is given by pi d to the power of 4 by 64 now. Similarly, the moment of inertia possessed by the cutout circle, which is having diameter is equal to small d, is given by pi d to the power of 4 by 64 now. Then the moment of inertia, this pi d to the power of 4 by 64 and this pi d to the power of 64, these two are representing the moment of inertia possessed by that main circle as well as the cutout circle about the x-axis, and also the same values having about the y-axis now. Hence, the moment of inertia of the hollow circular section is obtained by taking the difference of moment of inertia possessed by the main circle and the cutout circle now, which is equal to, that is the Ix is equal to pi d to the power by 64 is the moment of inertia possessed by the main circle, and minus is pi d to the power 4 by 64, it is the moment of inertia possessed by the cutout circle. This difference values is giving the moment of inertia of a hollow circular section about the x-axis. Since pi by 64 is the common word now, the remaining value is equal to capital D to the power 4 minus small d to the power 4 now. Similarly, Iyy is equal to That is the moment of inertia possessed by the alveolar circular section about the y-axis. Since the object is symmetrical about the x-axis and the y-axis, hence we are having I-axis is equal to I/y. So by using the relations we got to I/y is equal to pi by 64 into capital D to the power of 4 minus small d to the power of 4 now. The moment of inertia possessed by this hollow circular section about the z-axis is equal to I z is equal to, which is equal to I-axis plus I/y. Since I-x is equal to I/y, both are there now, that it can be written as now 2 I-x now. Hence, we can take it as now I/z is equal to 2 into pi by 64 capital D to the power of 4 minus small d to the power of 4. Since it is equal to pi by 32, we can take it as d to the power of 4 minus small d to the power of 4. This is the moment of inertia possessed by that alveolar circular section about the z-axis. These relations holds good only if the center of the main circle is constant with the center of gravity of the cutout circular section with each other. Now the moment of inertia of a triangular section. Let ABC is the given circle. B is representing the base of the triangle and H is representing the height of the triangle. Now let us find the moment of inertia possessed by the triangular sections about the line BC, which is also called about its base now. So let us consider small strip PQ, which is at a distance of y from the base as shown in figure now. The strip having thickness is equal to dy now. Let the breadth of the strip is equal to, assume it is equal to b1 now. Now the area is represented now. Small area possessed by the strip is equal to length breadth b1 into thickness is equal to dy required now. So in order to find the b1 values, that is the breadth of the strip consider, is obtained by considering the triangles ABC, ABC and APQ as similar triangles. When they are similar triangle, the ratio of length of corresponding sides is always equal. Hence, according to the relations now, we can write it now. PQ divided by BC is equal to the height of the APQ triangle is given by h minus y, that is h minus y divided by h value. RPQ is equal to B1, we have taken, it's equal to BC into h minus y divided by h. R B by h, we can take it as h minus y. This is our length of the strip PQ, which is considered at a distance of y from the base now. That is PQ is equal to, we can take it as B into h minus y divided by h now. Now area of the strip is equal to this PQ, that is the length multiplied by its thickness now, that is B1 into dy. B1 is equal to B by h, h minus y into dy. The moment of inertia of the strip about the line BC is equal to area multiplied by the square of the distance between these two lines now, which is equal to y we have taken. That is b into h minus y by h into dy. This is the nothing but area multiplied by the square of the distance, which is equal to now b by h. It is a common word now. H minus y into y square dy now. Or on multiplication we got to b by h y square dy minus of y cube dy now. This is the moment of inertia possessed by the line PQ above the line BC now. The total moment of inertia possessed by the triangle above the line BC is obtained by doing the integration of above equation from 0 to height of the triangle, that is 0 to h now. That is IBC is equal to b by h into 0 to h y square dy minus half y cube dy. So b by h, and applying this, doing the integration, hy square dy integration is hy cube by 3 now is given, minus y cube dy integration is given by y to the power of 4 by 4 is given, and applying this limits 0 to h now. So b by h cube by 3 minus h to the power of 4 by 3 minus h by 4, h to the power of 4 by 4, and doing this, b by h is a common word and 12 is the LCM for this now. The remaining values now becomes 4h to the power of 4 minus 3h to the power of 4, which is equal to bh cube by 12. This is representing the moment of inertia of the triangle about the line BC or about its BC now. Okay, sometimes we required to determine the moment of inertia of this triangle about its centered axis now. The centered axis always lies at a distance of h by 3 from its base now. That is here this distance is equal to h by 3 required now. H by 3 we required. So if it is the GG line is there now, that is which is passing through the centroid. BC is representing the base now. So IBC is equal to, we can take it as IG into IG plus area multiplied by the HC square now, where HC is nothing but representing the position of its centroid with respect to the base now, which is equal to IG plus A h by 3 whole square now. So by using this equation, we can determine the moment of inertia possessed by the triangular section about its centered axis also now. So from this relations we got to IG is equal to IBC minus of A into h by 3 whole square. So here this is the relation. By substituting the values of IBC is equal to BHQ by 12, area is equal to, area of the triangle is equal to half of the product of base into height now, and HC is the representing position of centroid from its base is equal to h by 3 whole square, which is equal to BHQ by 12 minus BHQ by 18. Okay, on simplifications we got to 36 is the LCM, that is BHQ by 36. This is representing the moment of inertia possessed by the triangular section about its centroidal axis. Now the moment of inertia of a semicircular section now. Let ABC is representing the A, B and C is representing the circular section. Let R is representing the radius of the semicircle. The moment of inertia of semicircular section about a line AB, that means diameter of the semicircle is equal to the half of the moment of inertia possessed by the circular section now. But the moment of inertia of circular sections about its diameter AB is obtained by pi is equal to pi divided by 64 into d to the power of 4. So by substituting the values, since the half of the circle is there now, which is equal to IAB is equal to pi d to the power of 4 by 64 into 2, that is equal to pi r to the power by 128 now, pi d to the power of 4 by 128, which is equal to pi r to the power of 4 by 8. On simplification, we got to 0.393 r to the power of 4 now. The moment of inertia possessed by the semicircular section about its centroidal axis now. The centroidal axis always lies at a distance of, since the object is now symmetrical about the vertical line now, the centroid lies always on the same line at height of 4r by 3 pi now. That is the position of the centroid of semicircle lies at a distance of 4r by 3 pi from its diameter now. So according to the figure now, the area possessed by the semicircle is equal to 1 by 2 pi r square now. H is equal to 4r by 3 pi. By using the equations, IAB is equal to IGG plus AH square, where IGG is representing the moment of inertia of circular section about its central axis. IAB is representing the moment of inertia about the diametrical axis. Hence, IGG is equal to IAB minus AH square now. Okay, by using these equations, we got IG is equal to IAB minus AH square. IG is equal to pi r square by 8, already we determined in terms of radius, minus 1 by 2, this is the area, multiplied by the distance 4r by 3 pi, whole square we required, equal to pi r to the power of 4 by 8 minus of 1 by 2 pi r square into 16 r square divided by 9 pi square. On simplification, so we got to 0.11 r to the power of 4. This is the moment of inertia possessed by the semicircular section about its center of gravity. For the quarter circle, the moment of inertia is equal to 1/4 of its circular section. That is, IAB is equal to the moment of inertia possessed by the circle is given by pi by 4, pi by 64 d to the power of 4. So, semicircle, that is the quarter circle, is given by, it is 1/4 of the circle, which is equal to pi d to the power of 4 by 64 into 1 by 4, which is equal to pi r to the power of 4 by 16, or it is equal to 0.186 r to the power of 4 now. Now about the centroidal axis, since the centroid lies at a distance of 4r by 3 pi from its diameters, by using the relationship we can determine the moment of inertia possessed by the central axis is given by 0.055 r to the power of 4 now. Okay, these are the summary of the moment of inertia possessed by the some regular sections about its central axis. That y-axis is equal to, for the rectangle, it is equal to bh cube by 12. For the triangle, it is equal to bh cube by 36. For the circle, pi d to the power of 4 by 64 and so on. And also, for the semicircle, it is equal to 0.11 r to the power of 4. And similarly, for the quarter circle, 0.55 r to the power of 4. And ellipse, it is equal to pi a b cube divided by 4. About its x-axis, about y-axis is equal to pi b a to the power of 3 divided by 4 now. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.